not record now. I hadn't turned it on there before, so but we'll be going on from here. We'll be on from here on. Okay, so where's an industrial hygienist likely to turn up? Hazardous waste sites, schools, homes, industries, police departments use extensive use of hazardous industrial hygienists. For instance, they have gun ranges where policemen have to practice their operation of their weapons. Military involves, of course, all sorts of hazardous environments. Medical profession. We just saw someone on chat that was talking about how they do rounds in evaluating the risk that and training people on minimizing risk in a medical environment. Pharmaceuticals, emergency planning, most everything you can think of, an industrial hygienist might be involved in. So to summarize what I would tell people at these parties is I would tell them basically my business is mostly responding to hysteria. In other words, anytime there's something that hits the newspaper, Legionnaire's disease, PCBs, mold, asbestos, anything that comes up like that, there's an industrial hygienist involved in the middle of the mess, right? They may not make the mess, but they certainly get involved in it at some point or other. Okay, so recent example, for instance, New York City had a serious outbreak of Legionnaire's disease associated with cooling towers in August of 2015. Over the course of a year, they adopted a new law, local law, that requires very exhaustive monitoring, risk assessment, treatment, sanitizing of cooling towers, these big water devices, big water spray devices that they use on air conditioning equipment. In order to do these risk assessments, in order to support companies, buildings, so on and so forth, in assessing the risk and making sure that the environment is safe, you have to be a qualified person. So they defined a qualified person to do this kind of work as a New York State licensed and registered professional engineer. Most states register engineers and architects. A certified industrial hygienist. There you are. You turn it up right there. Certified water technologist with training and experience developing management plants, and an environmental consultant with at least 2 years of operational experience in water management and planning. Now look at that. Certified industrial hygienist, you'll go through this whole program. We may never discuss cooling towers again. Yet they have a level of confidence in the idea of a certified industrial hygienist, level of confidence that that person has the training to do this kind of work, that they included them, even though they may not have direct training in cooling towers. They included them because they figure that's kind of training that would allow you to really understand what's needed and learn what you need to do about that kind of environment. Okay, so a lot of environments. Here's a couple. One person on one side there's probably doing some sort of indoor air quality evaluation. Looks like she's using a pump to sample the air. Person on the other side has a hazardous waste site, maybe an emergency response or something of that nature. Okay, many different materials. We're dealing with, I already mentioned, PCBs, dioxin, lead. For instance, here, lead paint. Anybody know what that stuff on the left side there is? I'll wait for a response. Who wants to take a wild guess on what that stuff on the left is? I'll give you a hint. The picture of those guys on the bottom and the picture of that stuff in the pink there's an association between them. Give me a guess. Right, exactly. They're both anthrax. That's anthrax the group, and that's anthrax the bacillus. Okay, good. So we're dealing with microbiological contaminants, physical contaminants, airborne materials, and so on and so forth. So many different materials that we're going to be working with how we approach the collection of samples, the analysis, the working with labs, and so on and so forth. How we approach that for all these different kinds of things. Okay, a lot of times we're dealing with very, very small quantities of toxic materials. Okay, so for instance, when we're concerned about a worker's exposure to particulate materials, that could be silica in the air as he's working, as he's repointing brick structures, or as he's working in the Midtown Tunnel. to scrape off all the old tile, and grind off all the old tile, and install new tile is exposed to a very dangerous dust that includes silica, for instance. So we're concerned about exposure to small particles, especially small particles. And we know that a worker breathes about 10 cubic meters of air during an 8-hour day. So we know an average person does about 20 cubic meters per 24-hour day. And we can imagine what a cubic meter is, right? A volume of air that's 1 meter by 1 meter by 1 meter. Or you could also look at it as 10,000 liters. Okay, so you can figure that out, cc's and so on and so forth. You can figure out the dimensions there. So you see how much air that we're breathing in. If that air has dust in it, that dust is going to wind up in our lungs. Here's a diagram. I'm sure you've seen this before, a diagram of how our respiratory system deals with and is exposed to particles of different sizes. As you breathe in, the largest particles are going to be trapped within your nasal pharyngeal area, in your throat, and so on and so forth. And then as the air breaks up and hits the bronchi and the various other structures in your lungs, the air then has to change direction frequently and speeds up as it goes through these smaller and smaller channels. And what winds up happening is that the particles impact on these surfaces and get stuck there. But the smallest of the particles, let's look all the way down here, these sub 2.1 micron particles, they go way down into your lungs, into the bronchi and the alveoli, and can really affect surfaces of your lung that are involved in direct transfer of gases. In other words, really sensitive living tissue. So we're really most concerned not so much about the biggest particles, where we really trap them in our nose or our throat or something like that before they can really get into our lungs. In other words, particles bigger than 10 microns, which a lot of times industrial hygienists term non-respirable. We're really most interested in respirable particulates under 10 micron, and particularly those under 2.5 micron. Okay, well, the ones that get down here way down into your lungs. So we're focused on very low concentrations because we're dealing with dangerous materials, and we're focused on very small particle sizes. Here's put it into perspective a little bit. Here's roughly a human hair, pretty nasty looking hair, and roughly what these different particle sizes look like. These are microns, basically stand for microns. Okay, and so for instance, particles that are less than 10 microns, a hair is about 50 to 70 microns. So it's about a fifth or a seventh of the diameter of a human hair. Anything less than that would be considered respirable. And the ones we're most concerned about are the ones that are even like much, much smaller than here. And you can kind of see them demonstrated there. There's also a combination of fine beach sand. So in case you're wondering, well, how come I don't get silicosis from going to the beach? It's because the particles are so large, right? So they're less hazardous than some of the materials that you might wind up in a work environment. Okay, so yeah, we just saw that already. Okay, we're also looking at very low concentrations. So for instance, the way we might describe exposures is going to be for particles, it might be the weight of those particles per cubic meter of air. So this number, 5 milligrams per cubic meter, anybody know why that number is particularly important? Why I brought that number up? Why did I pick 5 milligrams per cubic meter to focus on in terms of like dust? That's the OSHA standard. That's the OSHA permissible exposure limit for otherwise unregulated particulate. In other words, what we used to call in the old days nuisance dust. Okay, any other kind of dust that's regulated by OSHA is going to have a limit that's less than that. So that is like the biggest amount of dust that you could tolerate for anything, pretty much, in a workplace per cubic meter. So per 10,000 liters of air, only 5 milligrams. Well, what does 5 milligrams look like? Okay, well, let's get a handle on how small a quantity this is. This is familiar. How many of you guys use Splenda instead of sugar? I know, there's a T-shirt, there's a shirt going around says you never see a skinny person drinking Diet Coke, right? Which pisses me off because I'm not a skinny person and I drink Diet Coke. But at any rate, I'm pretty familiar with this packet. I suspect some of you might be familiar with this packet. Okay, if you look down here, what do you see down here? How much powder by weight is in this packet? Okay, it's 1 gram. I'm kind of throwing out kind of questions that you can respond to if you want. You don't have to respond to them, but I don't want, the problem here is that I suspect that the interaction here by typing into the chat box might be a little slow. So I don't want to slow down too much. But I also want to give you an opportunity to give me a little bit of feedback on what your opinion or what you might know about this stuff already, or if I'm going too fast or too slow. So this packet, familiar enough Splenda packet, holds 1 gram of powder. That's what a gram of powder looks like. Just simply emptied out onto a dark background. Okay, that's 1 gram of powder. Okay, we're talking about 5 milligrams, 5/1000ths of a gram. Just a little bit of background: a nickel weighs about roughly 5 grams. A dime weighs roughly about 2.5 grams. Okay, so I'm going to take that powder and I'm going to take out my credit card and I'm going to divide that in half. And I don't want to hear any tittering about this use of the credit card to divide this powder like that. Okay, trust me, I've heard all the comments before, and I apologize I didn't have a $100 bill to do it with. Okay, so next, I'm going to divide this in half. Now, once I've divided this in half, I have 500 milligrams. Obviously, half a gram. That's 1,000 milligrams in a gram, 500 milligrams. That's half that powder. Okay, that's also 500,000 micrograms, right? So it's 500,000 micrograms, same thing as 5 milligrams, same thing as half a gram. I'm going to divide it again. Now I got 250 milligrams and 250,000 micrograms of this powder. Okay, again, I divided again, 125 milligrams and 125,000 micrograms. I'm not going to keep you watching me do this forever, so I'm going to go down here. This is what I'm left when I divide it up enough that I'm down approximately where there would be 5 milligrams. You could also term that as 5,000 micrograms. That's the amount of dust that would be the most for almost any OSHA PEL that you could have in a cubic meter or 10,000 liters of air in a workplace. That would only be nuisance. That would have to be distributed through that whole 10,000 liters of air, right? So we're measuring dust in air, particles in air, asbestos particles in air. We're looking for really small quantities. And anytime you look for small quantities, you have to use special techniques. We're going to learn about it. By the way, let's take a look at another one here. This is 250 micrograms. Can you see it there? It's kind of like a little tiny pile of power, based on just half and half and half and half. I got it all the way down to 250 micrograms there. That's what that looks like, a little tiny pile of powder there. Okay, why did I pick that out, right? That particular quantity out. Well, let's take a look at something here. The OSHA, the New York City Health Department action level for lead in a small child's blood is 5 micrograms per deciliter of blood. A deciliter is 1/10 of a liter. Okay, so 5 micrograms per deciliter. 5 micrograms is 0.005 milligrams, which is 0.0005 grams per deciliter. Okay, so we're looking at 5 micrograms per deciliter of blood is the action level, the point at which they're concerned that that child might be lead poisoned and that they need to monitor that child. Okay, so now it used to be when I was a kid, it was probably 25 and they probably didn't test anyway, and there was lead all over the environment. And that's why I don't have a PhD now. Okay, that's the reason. It has nothing to do with not wanting to put in the work. Okay, so let's take a look at our little pile of powder there represented 250 milligrams. Well, how does that relate to that 5 micrograms per deciliter? Let's take a look at this. New York City screens small children when they enter the first grade. They have to go to the doctor, they have to get a blood test, and get, among the other things that they're tested for, they're tested for lead. Okay, small child, the average size might have 5 liters of blood. Actually, I'm being pretty generous when I say 5 liters of blood. Probably is less, right? So 5 liters of blood is the same thing as 50 deciliters. Well, the OSHA, the New York City Health Department says the action level is 5 micrograms per deciliter. So you got 50 deciliters times 5 micrograms per deciliter. For those of you that are not so comfortable with math and stuff like that, industrial hygienists very frequently will check their work by doing something called dimensional analysis. I think I can find out how many micrograms that you would have in 50 deciliters by multiplying 50 deciliters times 5 micrograms per deciliter. And it comes out to 250. And sure enough, deciliters cancel out here with deciliters, so you're left with micrograms. So I have a pretty good idea. I'm doing the right thing there. Okay, so 250 micrograms. Well, what does that mean? That 250 micrograms is how much, that's that little bunch of specks there. What's the long story? Long story short, maybe too late for that, right? That this amount of lead is sufficient to exceed the New York City Health Department's limit for lead in a child's blood. That's all it takes. Admittedly, that's different than what the child might get on his hands or how much you ingested, or how there's also the issue of how much that he ingests he would actually metabolize and get to blood, so on and so forth. But that's as much as he needs in his blood to be basically defined as blood poison as far as the Department of Health is concerned. Pretty amazing, isn't it? We're really dealing with small quantities here of materials that can do a lot of damage. Okay, so in addition to doing these kind of exercises and measuring these very small quantities, we need the assistance very frequently of laboratories in order to do this kind of work. Okay, so let's see what I have here. Let's see if I can see what I'm up to here. Okay, so we need some help from laboratories to do this kind of stuff. Now, we can't just use I'm just checking a text here that I got from you guys. Okay, so at any rate, let me go back here. One of the things we're concerned about when we use laboratories is we want to make sure that the laboratory that we use is capable of doing the correct analysis, doing this analysis the way that it's supposed to be done, that they're accurate or proficient, and that they're consistent. That if you give them something, you'll get the right answer and they'll get the same answer each time you do it. It's certainly within certain parameters. Okay, now we don't have the resources to check their work, obviously, so we rely on other agencies to evaluate the proficiency of that laboratory. And those organizations could be American Industrial Hygiene Association, could be the EPA, could be the New York State Department of Health. Those organizations accredit laboratories. That accreditation process is pretty detailed. It involves setting up a manual, a laboratory manual for that particular facility, making sure, getting inspections, making sure that they have the proper equipment, they're using the proper techniques, their workers have proper training to do that work, that they have a manual of procedures that meet the accreditation organization's procedures for each different kind of medium and each different kind of contaminant that they're going to analyze. So they have to spend a lot of time and energy putting together these manuals, getting their equipment together, getting their training together in order to get accredited by one of these organizations. It's very expensive, very time consuming to set up an accredited lab. Okay, you don't see too many new ones. You see a lot of labs that are in business already that add accreditations and new medium and new procedures. I don't see too many new ones springing up too often, at least not anymore. Okay, so part of that process is even beyond that, even if they have got their accreditation, they have to make sure that laboratory continues to do accurate work. Okay, and so that laboratory has to do quality control. They have to do their own quality control. They have to test samples that they know are standards, make sure that their procedures get the right answers. And even beyond that, they can't just rely on their own quality control. the organizations that accredit them frequently use proficiency testing to make sure that the results are accurate and reproducible. So, for instance, New York State has an environmental lab and accreditation program. Okay, and that program sends samples, lead in drinking water samples, for instance, asbestos samples, well, maybe not asbestos samples, but other kinds of samples, to these ELAP labs throughout New York State. And these samples are basically unknowns. The lab has to report on these, test these samples, and they have to provide their results back to New York State. In order to maintain their proficiency and their accreditation, they have to be within a certain range of the right answers on these. And if they flub too many of these samples, they could lose their accreditation, at least for a period of time, or at least until the state is satisfied that they've corrected any issues that they have. Okay, so here's a few of the accreditation programs. You can click on these. I put up a pretty close version to the one that I'm using right now, not 100%, but pretty close version to this PowerPoint that I'm using right now on Blackboard. You have both the PowerPoint and a PDF version of this. I'll make sure that before the night's over that you have the actual version that I'm using here as well. Okay, so here's a bunch of accreditation organizations for different. AIHA has an environmental lead program for air testing. New York State has one for drinking water, the ELAP, and so on and so forth. EPA has certified programs for wastewater testing and for drinking water testing under the Safe Drinking Water Act, and so on. And there's many other accreditation programs for different materials, different mediums, and different contaminants. Just recently, up until recently, in order to do Legionella testing in water, okay, now just keep in mind, Legionella don't just grow in cooling tower water. They also grow in domestic water system. In other words, your hot water in your home or your place of work, they also grow there as well. CDC had an accreditation program for laboratories doing Legionella testing. And New York State now has added an accreditation for Legionella testing to their ELAP program. In fact, New York State requires you to have their certification, their accreditation to do Legionella testing in New York City, not just the CDC certification or accreditation. Okay, yeah, you can get batted around by these organizations a little bit too. Okay, you have to do proficiency testing. AHA, individual accreditation. Okay, good. We kind of went through that. And these, again, this accreditation involves receiving these blanks or samples without anything in them, blind samples that are spiked with certain amount of material, and so on and so forth. Any of you guys ever take quantitative chemistry or qualitative chemistry, where you had to, where you would get at some point from the semester, for your professor would hand out a unknown sample if you were taking qualitative chemistry, and you had to figure out what was in there by doing a flow chart of tests and so on, or quantitative chemistry where you knew what was in there and you had to test, you had to titrate or test or otherwise analyze a sample and figure out what the concentration was. Anybody ever take a course like that? I expect some of you guys that have a medical background might have had some advanced chemistry courses. I'll wait for an answer and see if I get some. I'll wait a minute for an answer, see if I get somebody that has done that. Don't look like it, eh? Okay, well, they do that. So in some chemistry programs, they do actually do that. Okay, qualitative chemistry and quantitative chemistry. Okay, so all right. Oh, and by the way, in addition to what the laboratory is doing, we're going to be coming up later on our responsibilities here. Our responsibilities are to understand how the limits of the analysis, right? What methods the lab is going to be using, the limits of their analysis, and also how to properly collect the samples, how to properly label the samples to the laboratory, how to deliver them to the laboratory in the proper conditions, uh, 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 how to make sure that they stay within a chain of custody, that we know who's handling them, how they're handled, how they're stored, and so on and so forth. That's within our purview. That's within our responsibility. And there are organizations such as NIOSH that if we're doing, for instance, occupational health work and we're taking samples, that maintain manuals that outline for us the exact procedures that we have to use for doing a variety of many analyses. In fact, any of the OSHA PELs or most of the proposed limits or even most of the chemicals with TLVs have procedures that NIOSH has published on precisely how to do these analyses. In the next couple of weeks, we're going to be using a NIOSH procedure that involves the measurement of particulate material in air. Okay, so we'll actually look up that procedure and we'll apply that procedure using the right equipment, the right techniques, the right calibration, and so on and so forth. I'm going to I'm going to back out in about 5 minutes. I'm going to back out. I'm going to show you a typical chain of custody and maybe something that'll kind of give you an idea on the results of some proficiency testing. Okay, methods. There's a number of organizations that publish methods for these analyses, procedures, very strict, specific procedures. Here's a bunch of them. I mentioned NIOSH's procedures, analytical methods for samples that involve occupational exposures. There's also American Waterworks Association, American Public Health Association publishes standard methods for water and wastewater analysis. So there's a number of these organizations that you can refer to their methods for their published methods for how you should handle, and have samples analyzed. Okay, and I'm going to show you. I'm going to give you a couple of examples of this rather than, I think, getting into too much detail on these standards, which we can I can give you links to and you can look at. Okay, so now let's talk about these chemicals, these materials, these toxins that we might be concerned about. Biology and chemistry, yeah, okay. Oh, Lehman College, okay. So at any rate, let's talk about these materials that we might be concerned about, and what we want to know about them. Well, first of all, want to identify what they are, and often we're dealing with commercial products that have proprietary formulations, or the names don't actually describe what the material in them is, but we need to know their chemical names. Now, Chemical Abstract Service maintains a listing where manufacturers can identify specific chemical names by a number that everybody uses to identify that particular chemical. So very frequently, it's better to use that chemical abstract number, that CAS number, to identify a chemical rather than to check the identity of a chemical rather than the chemical name, because they can have many different names. Okay, MEK, methyl ethyl ketone. There can be a number of commercial names for that chemical. Acetone, I think, is methyl ethyl ketone. I think is acetone. Methyl. I don't recall. I don't want to be wrong, so I'm gonna back off on that. But there's a number of ways the nomenclature of chemicals can be pretty complicated. So CAS numbers will help you keep that organized. Make sure that you're working with this. So you know what you're working with. We have a number of organizations that define exposure limits. Okay, for instance, OSHA, their exposure limits are called permissible exposure limits. Anybody know what the time period is? There's a time period associated with a permissible exposure limit. Anybody know what that is? I'll wait for somebody to tell me. What's the time period that's associated with a permissible exposure limit? Is it something's that instantaneous reading? In other words, permissible exposure. If I go in and the worker's exposed to the solvent that I just mentioned, methyl ethyl ketone, if I want to test if the worker is exposed to above the PEL, permissible exposure limit, is it okay for me to just go in there with an instrument and take an instantaneous reading and tell you whether his exposure is too high? Somebody type in no, so I know that you're there. Oh, you got me worried now. I'm hoping you guys can hear me still. I'm going to wait for someone to type in no so that I know you're still connected. Thank you very much. I'm not sure if it's a lag in the chat typing, or if I put you to sleep already. You know what I'm going to do? I'm going to back off of this in a slide or two, and I'm going to go to a couple of things I have in the background. Then I'll come back to this. Maybe we'll even take a 5-minute break like we would in a real in-person brick and mortar class. Okay, so let me move on from here. Okay, just this gives you a rough idea what some of these analyses would cost and so on and so forth that you would get from these various labs. I think I might be able to rustle up a real detailed price list for you. But now there's a caveat here to all these prices. The prices for these analyses can be relatively inexpensive, very common, simple analyses from labs, or they could be very expensive. But all of these prices are probably assuming very short, very long turnarounds, like maybe 2 weeks. Now, if you want your analysis in a week, it's going to cost more. If you want it in a day, it's going to cost several times what any of these prices are. And if you need it the same day, which is not unusual in construction sites and so on and so forth, need it the same day, that can be very, very costly. Of course, you have to add to this the cost of taking the sample, the equipment that you need to take the sample, the paperwork that you have to handle to do this, the delivery of the sample to the laboratory in a timely manner and in the right form. So sampling can get very expensive. But customers love sample reports. They love something quantified. Sometimes industrial hygienists, because of their experience and their knowledge, they can evaluate risks better than just getting numbers, or more effectively, more cheaply than doing a lot of analysis, doing more analysis. But I have to admit, customers love numbers, and a lot of times they're willing to pay for them. So a lot of times you'll find yourself doing a lot more testing than you really think is necessary to evaluate the specific environment that you're concerned about. Okay, accreditation. Yeah, now what about accreditation? How do you know that a lab is accredited? Well, you can't just depend on them saying, I'm glad you brought that up. I forgot that I didn't answer that question, did I? Okay, the PEL is a permissible exposure over a period of time. It's an 8-hour time-weighted exposure, the average exposure over a period of 8 hours. Why does OSHA do that? Because most workers work an 8-hour day. So that's their real exposure. Their real exposure is not the high exposure for a couple of minutes and then almost nothing for the rest of the day. And it's not a very high exposure for half the day, but nothing for the rest of the day. It's the exposure over the course of the whole day. That's a permissible exposure limit. Those are set by those are actually part of the OSHA laws, the Federal Register, those permissible exposure levels. And in fact, it's very difficult to add to them or change them because it involves a change to the something that's going to the Federal Register, which is a congressional record, basically. Okay, so NIOSH has many more recommended exposure limits that aren't PELs because it's just too hard to get them into the Federal Register. A lot of people use a backup to the permissible exposure limit. They use TLVs, threshold limit values. Okay, and those are put together by an organization called the American Congress of Government and Industrial Hygienists. Okay, and that organization puts together committees Those committees involve industrial hygienists, safety experts, chemists, physicians, and people within the industry that use those chemicals. They are a lot less constrained. They're a private organization, a lot less constrained. That committee can evaluate the standard, the danger of the material. And while PELs are kind of negotiated, because PEL is partly a accommodation to what they think they can practically achieve. The TLVs are a little bit different. TLVs represent threshold limit value represents the level at which you start to see health effects. Okay, so it's a little bit different, right, in format. So TLVs, that means that level at which you start to see health effects. Okay, so in other words, if you're exposed to methyl ethyl ketone, you might say to yourself, well, below this level, we don't really, based on medical studies, exposure studies, we don't really see significant health effects at this level. But then if we increase that level, we start to see the beginnings of health effects. That point is a threshold limit value. Presumably, if you stay below that level, you won't see health effects, presumably, right? That's at least what the intention is. Okay, so that threshold limit value is different, and it's determined by a committee. It doesn't have to go through Congress or it doesn't vary by what administration is around at this particular time. So it's a very useful backup to the PELs. Plus, there's hundreds of TLVs, maybe even more than hundreds, but there's relatively few PELs because they're so difficult to get established. So it's a significant backup to this issue. Okay, methods reference, alternative methods. Now, the other thing we're going to be using quite a bit, and what we're going to more and more in industrial hygiene, is the use of on-site direct reading instruments. They could be as simple as devices that change color, tubes or tabs or things like that, or badges that change color on exposure. Or they could be very sophisticated instrumentation that measures the presence of very specific contaminants in the air. Okay, so at any rate, so I'm glad you brought up that PLV reminded me about that. Okay, so a lot of different ways that we can sample. Just before we do that, I want to back out for a second. And I just wanted to show you, let's see what we got here. First of all, number one, I'm going to go to a website. This is, and this should be in Blackboard. If it isn't, I'll make sure it is there. This is the NIOSH Manual of Analytical Methods. It gives you all sorts of background on measurement techniques, testing devices, filter consideration, so on and so forth. Within this manual is also a series of methods that you would use to do specific analyses. So, for instance, perhaps we wanted to analyze for ketones. Okay, methyl ethyl ketone, for instance. Say I want to analyze for ketones. I could go to, I think I'm going to be able to find HI, okay, let's see. I could go here to, by chemical name. Actually, you want to know something? I think it's going to be here, methyl ethyl ketone. It's right there, acetone. Listed with that. It's the same method for acetone, so it's listed with acetone. Okay, so what does this method look like? This method very specifically tells you, well, this one's in urine, okay, but there's going to be other methods for in air, volatile, in air, in water, and so on and so forth. Okay, so how is this done? Let me see if I got another. Ketones, here we go. Acetone, ketones, acetone, methyl. So this is in air. Okay, so how do we analyze for, that surprised me a little bit, excuse me. How do we analyze for ketones like acetone, like methyl ethyl ketone? By the way, why are ketones such popular solvents? Why are so many ketones used as solvents? Acetone, methyl ethyl ketone, really pretty hazardous ketone, MEK especially, neurotoxin, pretty nasty stuff. Why is it so popular? Anybody know why ketones so popular as solvents? I'll answer that. I'll make it a rhetorical question. It happens that the way ketones work is ketones are basically an organic molecule joined by one carbon with a a two, excuse me, a double bond to an oxygen, carbon with a double bond to an oxygen that connects two organic compounds. So methyl ethyl ketone is a methyl group and a ethyl group connected by this oxygen, a double bond to an oxygen molecule. And it happens that that oxygen molecule, that bond makes it a very polar molecule. And polar molecules tend to break things up. They tend to be very good solvents. For instance, you might be right now. I'm drinking something that has a polar molecule. That's a lot of people call the universal solvent, water, right? Very polar molecule. So at any rate, that's why methyl ethyl ketone is such a effective solvent. But it also partly also explains why it can be so damaging as well. So at any rate, so how do we actually sample for this? Well, we need a pump, right? We need a sampler and a pump. And this sampler is a tube that has silica gel in it. And it has we need a pump that's going to give us a flow rate of this amount. We need to collect a sample of this size in order to get a result that is within the range of the PEL. In other words, if I want something that's more that'll resolve the presence of this material at a level lower than the PEL, I need to take a larger sample. But a 2-liter sample is enough to have a resolution that will give you the a satisfactory answer for whether or not you've exceeded the PEL. And how do we do all this? Well, we have an extensive procedure, materials. There's instructions on how to collect it. There's math on how to do the analysis. There is information what lab equipment needs to be used, and so what other compounds it can be used for, and so on and so forth. So all this is very specific to how you're going. Here's a technique of gas chromatography or flame ionization detector, so on and so forth. So it's very specific in terms of the equipment that you need to use and how you actually do it. So that's a NIOSH method. Anytime we do an analysis that's going to involve an occupational health measurement, we want to go there and see if they have a procedure for it. I already opened that. That's the procedure. I don't need that again. Here's an example of some stuff that's been published on proficiency testing. It doesn't identify the labs, but you can see here that they gave samples, proficiency tests for this solvent in water. They gave proficiency samples to, let's see if I can figure this out. They gave this to 33 labs. And this is the results that the labs got for the sample that they gave them, which was a sample that was 15.2 micrograms per liter. This is the values that they got. And you see in the middle there, they're pretty close. On the average, they got pretty right. But as it turns out, 31 of the labs passed, and 2 of the labs failed, which means that those labs that failed probably have to repeat the proficiency testing. And if they fail again, then they're a little bit of hot water and they have to do something. Down here, and so on and so forth. See, I think there's 79 pages of the records on these proficiency tests. Okay, and there's one more thing I wanted to show you, and that is when you handle these samples and you deliver them to the lab, you need to properly identify these samples, tell them the techniques you use to sample them, let them know what kind of testing you want to do. For instance, this is a chain of custody for lead samples. You could be testing for lead in air, and you might have to know, they would want to know what method you want to use, what method you use, which would indicate what kind of sampling you did, and also what equipment they would need to do the analysis. You would check off which of those you need. These have certain reporting limits. This method is more sensitive. The graphite furnace method is the most sensitive method for determining lead in air, also in water. Wipes. If you have a surface and you're taking a wipe, you would use one of these methods. And if you can tolerate a reporting limit of 10 micrograms. In other words, it'll only be accurate down to 10 micrograms. It won't detect 5 micrograms, if that's good enough, and that is for many applications. You could check that. If you need a more accurate or a more sensitive test, you would check this and so on. But of course, you would tell them that who it's for, where the sample came from, what the date and time, and so on and so forth. Billing information on this side, so of course important. Sample identification, the location. If it was a wipe, you'd give them the area that you wiped. If it was a volume, you give them the volume of the air that you sampled, date and time sampled. And then equally important is the chain of custody. In other words, this is the person that took the sample and delivered it to the lab and the date that they dropped it off. This is the person at the lab that received it. So we know who had it, who took it, who had it, and who they relinquished it to, whose responsibility it was from that point. And you have a page for extra samples and so on and so forth. Okay, so I'm going to take a break. There are many different types of samples that we're going to be taking depending on what the medium is, type of material that we're sampling, and the analysis that we're doing. A lot of that's going to be determined by procedures that other people have developed, like NIOSH and American Public Health Association, EOHS, and so on. Okay, sometimes we might be taking one sample, grab a sample, take a sample of air, for instance. Sometimes we'll want to get an integrated sample. With PELs are a special kind of integrated sample. It's sampling throughout a period of time, and sometimes the samples have to go to a lab, and sometimes we have instrumentation where we can take readings and determine what these exposures are right where we are. Okay, so sometimes we're doing real-time monitoring. We actually look at a device and read what the level of oxygen in a confined space is, for instance, or the level of hydrogen sulfide is in a sewage treatment plant. And those devices, so very frequently, are monitoring continuously in real time, and sometimes they'll be recording the levels. Some of them are capable of recording the information. In the old days, we used to record it onto a paper tape or printer. Nowadays, most of these devices have built-in memory, so that you can download the information, you can store it, you can plot it graphically, and so on and so forth. Direct reading instruments that'll do real-time reading. Most of them have electronic displays or outputs. Again, they have data logging as well. There's also you've seen this twice now. This idea of colorimetric tube. They're basically materials, almost like litmus paper kind of things, where you can expose materials to an atmosphere, and they're designed to change color, for instance. And the intensity of color or the length of the color in the tube determines the concentration that might be, say, in the air. Bulk samples, very frequently you might take a sample of soil, dig up an actual quantity of soil, or take a water sample of a certain volume. Those are basically bulk samples. New York City Department of Health requires that if a lease changes and a new person is moving into an apartment, and the new family that's moving in an apartment has a child under a certain age, that the landlord is required to test that apartment, have it inspected and tested for lead. And the way that inspection is done is an industrial hygienist goes in, who's at special licensing from the city of New York, goes in, inspects the painted surfaces, makes sure they're in good condition, but he also takes wipe samples. He takes a damp material that has no lead in it, say a baby wipe. Almost sometimes we used to use literally baby wipes, unscented baby wipes, and uses that to wipe a area that's equivalent to about a square foot of a floor or a windowsill or a door or a door hinge, a door jamb surface or something of that nature, and take that wipe, put it into a protective medium like a baggie, and send it to a laboratory along with information about what the surface area was that he sampled. And those wipe samples the laboratory determines how much lead is in the dust that were on that surfaces. And if they exceed a certain amount per square foot, then the landlord may have to do some remediation work before that family is allowed to move in. In worker situations, frequently you have to make a choice. Are we interested in sampling the air in the area where the person works, or is it more appropriate to sample the area actually in the breathing zone? And we have special equipment and techniques to be able to sample the actual breathing zone of that worker, the area in the area within a few inches of his face, where you know that you're sampling exactly what he's breathing. Okay, we have pumps that we use. We're going to come across a couple of pictures pretty soon where we have sampling pumps, and we're going to be doing with this in the first couple of labs that we're working on. We have sampling pumps that we use to pull air through a collection medium. Remember, we had very small quantities of dust, very small quantities of volatile chemicals in the air, very low concentrations. Well, it's hard to measure that's very small amounts of dust, very low concentration. So what we do instead is we pull air through a medium that's going to capture the dust or going to absorb or capture the volatile organic chemical that might be in the air. And we use tubes with sorbent material, sometimes as generic as activated charcoal, sometimes other materials. And we use a pump to draw a precise amount of air through that tube so it can absorb the contaminant from that tube. For instance, if we pull 20 liters of air through a tube, send it to a laboratory, and they tell us how much acetone in the air, we can then figure out how much acetone was present in a cubic meter of air, and how much acetone, what the concentration was of acetone in parts per million. And we can compare that to the OSHA standard and see if the PEL has been exceeded. That kind of application with these tubes, we need the air to move through the tube slowly so it gets a chance to get absorbed on that sorbent material. So in that kind of situation, we use a very low volume pump. It's very precise, but it pulls air through very slowly. If we're dealing with a particulate material, we use a cassette that has a little paper filter in, not paper, but a special material filter in it to capture the dust. So if we pull 50 liters of air through that filter and we weigh that filter before and after we pull the air through it, well, the dust we've accumulated for those 50 liters by filtering those 50 liters of air is a difference between the weight of those two filters, the filter before and after. And then since we know we took 50 liters of air, we can predict how much there would be in 10,000 liters of air, or in other words, a cubic meter. Again, so we can compare to the standard. The highest flow pumps are reserved for asbestos sampling because we're concerned about very, very, very low levels of particles where asbestos is concerned. In fact, we don't measure asbestos contamination in the air by the weight. We measure it by the number of asbestos particles per liter or per cubic meter. And then there's also on the street every once in a while, you'll see that the city plants these test stations so they can compare the conditions of the ambient air, outdoor air, to the EPA's ambient air quality standard. You'll see these things in cages, chained up somewhere every once in a while for a few days. And they're using very high volume pumps to sample soot and particulate and other contaminants that might be in the air that are part of the basic ambient air quality standard. Okay, so the filter cassette that I described, that's a gravimetric test. If we were in person, I'd probably be holding one of these things up. Okay, the asbestos would be a filter where we would then take that filter, examine it under the microscope. We're going to be doing some of this as the semester goes on. Metals, we might be doing wipes. We might be sampling the air. Might be present metals that could be dissolved in water. We might be taking water samples. So we're going to be using a variety of tools, different cassettes, different sampling, different sorbent tubes, so on and so forth. Some of them, you'll understand what this means, open face and closed face, once you have your hands on them and you're holding these cassettes and these sampling devices. Okay, here we go. Here's some pictures right here. So for instance, these cassettes, these holders, those are meant, you can see them down here as well, those are meant for sampling particulates in air. In the middle of this set of this cassette is a filter. And as you use a pump to draw air through it, the particles get trapped on there. So then you can use a gravimetric technique, measure the difference in weight before and after you exposed it to that amount of air. So you can predict how much air was present in the air that the worker was exposed to. This device in the middle is a holder for these cassettes for gravimetric analysis. Except this one has a device. There's a little slot on it, and the pump connects to the other end, and air gets sucked in here and spins within this device. Thus, it's called a cyclone. That spinning effect actually makes the larger particles drop out into this little red reservoir over here, and only the smallest particles, the respirable particles, are carried past the filter where they're captured. This is a modification, so you can use this device to measure total particulates, and you can use this device to measure respirable particulates. Now, these tall, long devices are used for asbestos sampling. Okay, and these are 37 millimeter, these are 25 millimeter. The main difference is the length of the tube that's used for sampling. Anybody want to hazard a guess? Some of you guys may have been refugees from companies that do asbestos testing. Can any of you tell me why these asbestos tubes are so long compared to the gravimetric tubes? Anybody want to volunteer a guess? So I'll go ahead and answer that question. Okay, if I get ahead. Oh, okay, to measure. Okay, well, not so much. You got the right idea. You're kind of right on the mark there, except that it's a little. You got the right idea. It has to do with the fact that with asbestos, we're not doing gravimetric analysis. We're counting fibers, right? So you got exactly the right idea there. But the real reason that they're so long, that they're this shape and they're so long, is because the filter at the back here, when we take that filter, when we're done, we're going to examine that under a microscope and count the fibers that are on that filter. When we have a cassette like this, and if we use it closed face, if we just pull air in through here, a lot of the particulate gets deposited unevenly on that filter. But we don't care if it's uneven because we're just going to weigh it anyway. But when we we send a sample to a lab to analyze or examine under a microscope that filter for asbestos, that filter is so large, that filter is so big, they're not going to be able to count every fiber, every asbestos fiber that's captured on that filter. So what they do is they randomly select 20 or 30 small areas, tiny areas, count the fibers there, and then they average it for the average of the entire surface of that filter. So that means that it's important that the deposition of filters be even on this filter so that the lab is not fooled by the filters piling up in one spot, right? So, and the reason for the length is so we get a nice laminar flow through this filter so that the filters are evenly deposited over the entire length of the filter. Okay, so there's a reason, even just the shape of these things, the material, these are anti-static, for instance, so the fibers don't cling to the sides and not make it to the filter. So the shape, the materials, all of this has been carefully thought out. And we don't have to invent this, it's all in the methods. These are what these sorbent tubes look like. For instance, these tubes right here are probably activated charcoal tubes. Okay, I wonder if you might notice that some of these tubes have sections in them. There's a section here, there's a larger section here. Even these activated charcoal tubes, if we could see them a little bit more clearly, would have a big section and a small section. Anyone who has it, and the air would go through here, the sorbent would get captured here on this sorbent material. But then there would be a barrier and there would be a separate section. Anyone want to hazard a guess as to why there's two sections in this tube? The air direction is going this way. Okay, the big sections first. Anyone want to hazard a guess? And the activated charcoals also have 2 sections. Okay, again, I'll take that as a rhetorical question. Reason for that is that if we're sampling an environment that has more of a solvent or contaminant than we expect it to have, it's possible you might saturate this section that you're taking the readings, that you're going to use for taking your readings. Well, what the laboratory does is analyzes both of these sections separately. So it uses the front section to actually measure how much of the material was in the air. The back section is only there because the expectation is that if you did this correctly, low enough flow and a small enough quantity, that you would not find any in the back section. It would all be captured in the front section. But if we get any into the back section, it means you were blowing air through fast, or you saturated the front section. So all of the material didn't get caught in the first section. So you can't rely on this tube to have to accurately give you the concentration of air, the concentration of solvent in air, because you saturated that section. Okay, oh, there was a good picture of it. Right, there you go, front and back section for a activated charcoal tube. These devices are called these devices are called impingers. We used to use these for reactive gases and things like that. For instance, let's say you're using muriatic acid, hydrochloric acid, you're using chlorine or some other material. Well, just maybe just a general acid gas. You're concerned about too much acid gas, nitric acid, sulfuric acid, they're all gases really dissolved in water, that too much of these acid gases are getting into the air. What you could do is you could make up one normal solution of sodium hydroxide, an alkaline material, and put it in this tube, put it in these tubes. And what you would do then is hook up a pump here, and that pump would pull air down into this liquid. There's tiny little holes in this tube here. Air would come out of these holes and then exit through the side arm to the pump and so on and so forth. So what would happen is that as the acid gases came in here, they would react with the caustic soda or sodium hydroxide, neutralize some of the sodium hydroxide before they leave and go through the pump. Well, what would that mean? That means if you went back and took the liquid and measured how much sodium hydroxide was left, you would then be able to predict how much acid gas must have been in the air that you pulled through here. So these are called impingers or absorbers, right? In fact, they have very small ones. You can actually hang one of these on a worker's collar and put a battery-operated pump on his belt, and it's small enough that he could wear it for a period of time. Those were called midget impingers. Okay, there's a very bad, nasty joke about industrial hygienists and midget impingers that I'm not going to bring up now. Okay, here's a impinger built into a pump. This would be the kind of pump that you would use for general purpose. This one happens to have an impinger on it. You could use the same pump without all this, without this device to connect to a cassette for particulate measurement or a cassette for asbestos measurement. Here's a whole collection of devices that in special environments, if you're measuring sediments in the ocean floor or lake floor. This device that he's using here is called a thief. You can put your hand over one end of it. You can lower it into any depth, almost like using a straw, holding your hand over a straw when you dip it into a drink. If you release your hand, the liquid will come back up the straw to that level, and you can use this to sample what's in this drum at different depths. Okay, it's called a thief. In fact, people in the wine industry use this to sample wine in barrels. Okay, and they use a small version of this thing, so they can pull a sample out, put it into a glass, and smell it, taste it, test the alcohol concentration, and so on. In that case, it's called a wine thief. Okay, core samples. You can use this and jam it to the ground. You can see that there's a sharp edge there that you can twist. You jam it into the ground, twist it, and you can get a sample of soil and you can analyze the soil. Either use this as a composite sample to find an average amount of, say, some contaminant in that 6 inches of soil, or you can use it to examine different depths of soil to see if there's some here but not here, and so on and so forth. These sampling devices these are a couple of typical sampling devices you would use, say, to lower into a body of water, or a large tank storing chemical or something of that nature, and you could have something connected to these gates, these valves on the side. So when you get a certain depth, say halfway, you can tug on this one. It opens up temporarily opens up this valve. The liquid flows in here. You capture it at that depth. You lower it a little bit more, then you open this one, and you can get samples at two different depths with this particular device. So, whoops, I guess that's the last of my slides. See if there's something else here I want to show you. No, I don't think so. Just go back here and make sure I got to it. Yep, that was slide 44. Okay, so well, hang on a second. I got some more here. Yeah, here we go. Okay, another one of these sampling devices. Remember we mentioned grab samples. Sometimes, in some situations, for instance, let's say you have a client that's complaining about an odor in a space, but the odor is very intermittent. So you can't just go there at the drop of a hat and set up a pump and a sorbent tube and so on and so forth. One of the things you might consider is a technique called grab sample. And these samples, the way that they work is these are Tedlar bags, and these are stainless steel containers. And the way that this works is that, for instance, these stainless steel containers, they can be evacuated, flushed out with pure nitrogen, and then evacuated so that there's a very strong vacuum, very little material in them. And you can give those to someone who can go to a job site, and when the odor occurs, for instance, they can open up the valve, suck air into them, close the valve, and then return it to the laboratory for analysis, for GC analysis or mass spectroscopy or so on and so forth. So you can analyze air for VOCs using a technique like that. You can even maybe train a customer to take a sample. So when a intermittent odor occurs or an intermittent problem occurs, they can test it right there. These Tedlar bags, you can do a similar process with these, except of course you need a pump, you need a device to fill them. Where this is pretty passive. You just have to open a valve. You can even, some of these are designed so you can put a meter on these devices. They used to be called Suma canisters because that was the main manufacturer of these stainless steel containers that could be evacuated for sampling. You could add a special kind of valve to this, which is calibrated, a little needle valve, which is calibrated so it takes anywhere from, say, 15 minutes up to 8 hours for air to collect in this when you open the valve. So in other words, you could have a composite sample over a period of time captured the same way. Okay, so here we go. Here's some other considerations that you might be dealing with when you deal with samples. Type of containers that you use, how long you're going to store them. A lot of this kind of information will come from the laboratory where you're doing the analysis with. The labs themselves are enormously good sources of information on this. They will provide you with procedures. They'll provide you sometimes with sampling containers and devices. They may even rent you, and in some occasions, some labs will rent you the very equipment that you need to take the sample. So as the semester goes on, I'll give you, we'll try and accumulate a list of resources, for various different kinds of analyses. So you have a list that maybe you could go and use as a bid list or something like that to search for laboratories that would be appropriate to do work that you wind up getting involved in. Okay, so the labs themselves, if you go online to their websites, they will give you their particular procedure for handling different kinds of samples and suggest analysis. They also usually have pretty good technical support in terms of helping you to make sure that you do the work correctly and the samples that they get are valid when they analyze them. Okay, last thing I want to cover. You guys are going to have to write reports every once in a while. That's part of this part of the job. As they say, the job's not done until the paperwork's in. So inevitably, and I know we all hate writing reports, right? So inevitably, we're going to have some practice on how to write reports, how to interpret the data that we get, how to write a report and communicate that effectively to a customer or to your organization. Okay, cover page, typically it'll have company name, client name, dates, other information about why you're there, what the complaint was, so on and so forth. Now, inevitably, I know I always put an abstract in. Here they call it an executive summary or an abstract. Basically, it's a one-page summary, 1 to 2 page summary. What was done, where was it done, what you found, what your conclusions are, what your recommendations are. Okay, so why do you put that in there? The reason why you put that in there is because I am sure by this time we're an hour and 50 minutes in, hour and 45 minutes in. I probably put a few of you to sleep. If you can imagine, you hand somebody an 80-page report that's an accounting executive or a brokerage, a manager for a brokerage, they ain't going to go through that whole report. It's important that you structure a good abstract or executive summary so he knows what your conclusions are, knows what your recommendations are. And if he needs more detail, can go into the report and find the information that he needs. Of course, in order to find the information, he needs a table of contents, place where he can go to find what he needs. Okay, the body of the report is going to include the purpose, the reason why you're there, what the complaint was, the date, the time, the inspector, any certifications you have, your organization has, the sample collection, the methodology, basically, the sample analysis, including perhaps a table where you would summarize the results, and perhaps in an appendix, an actual copy of the lab report itself. Your interpretation of the results, your conclusion, and more often than not, your client is probably going to want some recommendations. Now, don't be disappointed if they don't take your recommendations. I can't tell you. I think my personal experience with this is that the more effusive and congratulatory on how good your report was, the less likely that the client is to implement your recommendations. However, on the other hand, the more likely they are to pay your bill quickly. So there is that consolation as far as that's concerned. So don't get disappointed if not everybody agrees with you or decides that they want to follow up on your recommendations. Okay, so you want to make sure you deliver what they asked you for. Okay, so this probably should have been up a little bit further in these slides, but you want to make sure that the report focuses on what the customer is asking you to do. Sometimes it might be appropriate to give a little bit of background on the contaminant or the environment or the risks associated with that, so that if they get the people that are working at that facility that are going to go past the executive summary have you acquaint them with some of the reasons why that your recommendations are valid and that they should be implemented. You should have a site description, where you took the samples, how you took the samples. If you do indoor air quality work, for instance, a lot of this information is particularly relevant. And you may find that there may be something to do with the age of a building, the type of structure it is, that might impact your results. That's information that in the future might be important when you go back to this report and decide what recommendations you've made. Okay, methodology as we spoke, and the results. Okay, results summarize. You should summarize those so that they mean something. Perhaps tables or charts that effectively communicate the information that you need to, and then an interpretation of that data that you're providing for. If you can if it's possible, this isn't always possible, but as much as you can, relate the results to known standards. If you're testing for something and there's an OSHA standard for it, a PEL or an ACGIH TLV, relate your results to what those standards are. Unfortunately, for many of the things you might get involved in, such as indoor air quality work, there is relatively little in the way of effective standards that you can compare your measurements to. Mold, for instance. Mold is probably the most effective ways to evaluate and inspect for mold is visually. Your eyes, your nose are the best tools for tracking down mold and your experience with this. In fact, in most cases, if you ask me how do you inspect for mold, I would tell you you don't inspect for mold, you inspect for moisture and water, right? And that's where the mold is, right? So you don't look for mold, you look for moisture and water. But the point is that they don't have a lot of standards for what's a problem level of mold or what kind of molds are most dangerous and so on and so forth. Most standards don't try to quantify mold exposures. Any mold is bad and should be abated or controlled. Okay, put in the conclusions, your recommendations, and perhaps also prioritize them to some degree. In the appendix, you have your lab results, the chain of custody forms. If you can get them, at least a list of the accreditation for the licenses for you and the firm you work for and for the labs that did them. I don't think anybody would actually put the licenses, copies of the licenses in there at all. Okay, final report. You want to make sure it's proofread carefully. Last thing you want to do is spend a lot of time and a lot of money, produce a $40,000 report that's full of typos and grammatical errors. So that report's important. Okay. Now we're going to do our own reports. We're going to do our lab reports. Likely that we're going to ask you to do 5 or 6 reports, on these various areas of study that we're going to be looking at. And those reports are going to, certainly they're a significant part of your grade, but when you look at this PowerPoint or this PDF file, we're going to be talking about this, especially as we get to the point where you're actually going to have to do a report or two. There's going to be a certain format that we're going to expect them in, and largely it's something that mirrors how you might organize a customer report, so that you have, or something that another hygienist might look at and be able to understand how and why you did things. Okay, so that's it. I think we're done. If you have any other questions, let me know. You can email me, and Grace just gave me, you pulled a hook out, right? So I can see I'm running just a little bit long. Grace pulled the hook out, pulled me off the stage. So I hope this was at least a little entertaining. And once we are in person and we're working with this equipment, we're going to have a great time, because this is a great course in terms of being able to get hands on and find out, use new devices, new instruments, and so on, and really do some pretty interesting stuff. Maybe even think of an interesting project for us to do for the end of the semester. Okay, so good night, guys. I will put this online for those of you that weren't able to watch the whole thing. I think most of this stuff we're going to be covering again in one form or another as we go forward. So good night.